called Logistic Regression. So this will open us up to classification tasks in machine learning, which is kind of exciting. So tonight, your outcomes are here. You should be able to implement logistic regression, and you should understand confusion in matrices, AUC and ROC curves. And you should also know how to kind of decide on the best logistic regression model and compare them. So to start, we're just going to import some libraries like usual. And as usual, my laptop takes forever just to import libraries. While that's loading, in this next part, we're just going to make a data set and then view it here in a data frame. There we go. So we just have one feature, and now you'll notice our target is binary. It's just a 0 or a 1. So this could be, yes or no, true or false. If you had two different groups, group 1, group 2. So we can visualize this data. So since it's binary, we get a plot like this. So our x is on the x-axis, and then we have either zeros or ones. So we have two lines at both of those locations. So now if we wanted to plot a linear regression to this, we can see kind of what we'd get. We get this through OLS, and then when we go to plot it, you can see that that's not really a good it did the best job it could, but that's not really going to capture what's in our data. So to capture what's in our data, we need a different type of function. We need a different shape of line that can fit that bar shape with the binary data. So what we end up using is what's known as the sigmoid function. It's basically an S-shaped curve. This is the formula for it here. So it's 1 plus e to the minus whatever value, and then 1 divided by that. And what it does is it takes any value and squashes it between 0 and 1, which you can imagine would work well when we have binary targets of 0 or 1. So now if we plot this, this is what a basic sigmoid curve looks like. So you can modify the sigmoid curve by basically giving a coefficient to whatever value you're passing in and also an intercept. So in this for loop, we change the values of I and j. And then on this line here, you can see xln is like our x values, and then I would be our coefficient, and then j would be like the intercept term. So this will plot out a few different graphs here. So you can see we can kind of move the sigmoid curve to the left or to the right. We can also make it kind of tighter, make the transition shorter, more of like a straight up and down line. So this is the data we're trying to be able to plot and to predict. So any kind of linear regression that we've done before, we can't really make this kind of line, how it's kind of like a Z or an S shape. So we need some other kind of function or transformation to be able to make a line that can mimic the shape of data. So it's on the x. It transforms all the x values to be between 0 and 1. It's because we want to do logistic regression, which uses the sigmoid function to take every x value and squash it between that 0 and 1. So, yep, so we can change the shape of it. We can move it to the left or to the right. So you could see we could kind of find the best function, the intercept and the coefficients, to kind of make it fit our data depending on where our values end up. So this is logistic regression. There's a lot of math involved behind it. The second section that goes over logistic regression goes into more depth on this. It has you kind of do it by hand. So I'd recommend you want to kind of understand more of the nitty-gritty details. But basically, it's based on probability. So it's going to give us an output, a decimal between 0 and for each of our x values that we want to make a prediction on. So if it's above the 0.5, then we're going to say it's a 1. If it's below the 0.5, we're going to say it's a 0. So it basically gives the probability that your whatever x value is a 0 or a 1. And so instead of predicting continuous values, we're not predicting price or any kind of continuous number. We're just predicting a 0 or a 1. And this task is known as classification. Even though we're using logistic regression is almost solely used for binary classification. So classifying between two different groups, yes or no, true or false. Sure. It's just when our target's binary. Because if we have a feature that's binary, it's basically just like categorical, and we can just have a variable for it. But yeah, so anytime you have a target that's one of two values, you always can use logistic regression. And this is like an important comparison to be able to make, especially as you go into interviews, the difference between a regression and classification task. So regression always predicts continuous values. Classification will predict a group that something belongs to. And we'll learn more about that in the future. We'll learn different models and techniques that can handle multiple classes and so on. So to use this, we're going to use sklearn. This is going to have the most of our machine learning models that we're going to use going forward. So we want to get familiar with it. So we're going to import it here. And then it's really easy to fit data to it. You just build a logistic regression here, and then you call fit, passing in your x and y. And then we're also going to plot our x and y again, and then we're going to make predictions here, so model.predict. And we're going to pass in just random x values from 1 to 5, just to kind of give us a range of where the predictions are going to lie. And then we'll see what that looks like. So we can see that that did pretty well at capturing and lining up with all the data points. You can see it missed a few on both the top and the bottom, but for the most part, it got the majority of them. So this is like the prediction line. You'll see in a second the actual sigmoid line that it came up with, and kind of what's known as the decision boundary. This is just plotting the prediction. So up until about 2.9, it predicts a 0, and after that, it predicts a 1, basically. So with our model, we can get our coefficient and intercept, like so. And now using that, we can use our sigmoid function and just some random x values. So basically multiply all the x values by that coefficient, add the intercept, plug that into the sigmoid function, and plot that versus our x values. Yeah, it's basically the same. Mx plus b for one feature is what you're going to have. And so when we plot that, we get our S curve that fit to our data that divides the two groups in the best way. What do you mean negative? Oh, but that's getting passed into the sigmoid function, so that gets transformed to between 0 and 1, basically. So if our x was 0, so in here, so if this was 0, our coefficient wouldn't matter. We would just take the sigmoid of -8, which if we do that, it's so model.intercept So the sigmoid of that -8 value is actually this. So it's very close to 0, but yeah, it squashes everything between 0 and 1. So then we got this sigmoid curve here. So basically everything below the curve becomes a 0 and everything above is a 1. So if we like picked the point right in the middle, that's kind of the break point. So everything above 5 would be a 1 and everything below a 0.5 would be a 0. Sure. Mm-hmm. So these are two different things. So if we go back, um, this is just predicting the values. So this is basically showing like where the cutoff point is. This isn't like the sigmoid curve. This is the actual sigmoid curve and what makes the decision boundary between the two groups. So it's not meant to kind of line up with the points. It's meant to divide them. Yep. All right, so that was with one feature. Now we're going to add two and see how that changes things. So we're going to make a random data set, view it here in pandas. So similar thing, we just have a second feature now. And we can plot this. And I color coded it. So group 1 is in blue, group 2 is in green. So you can see we clearly have two separate groups. They're in different areas of the plot. And on this plot, x1 is the x-axis, x2 is on the y. So now we're going to fit a logistic regression model to this data. And we're going to print out the coefficients because we have two different features now. So we're going to get two coefficients, and then the intercept is the same. There's only one. All right, so now we're going to go ahead and use those coefficients and that intercept to plot decision boundary of our logistic regression. Sure. Mm-hmm. So with linear regression, we were able to do it with basically just matrices, like the dot product and the inverse and all that. With logistic regression, the only way is through gradient descent. You can't do it with matrices. So you basically have to do it in an iterative fashion. So you could technically do it by hand. It would just take a lot more work, if that makes sense. Because we're including that sigmoid function, and if we're going to have to, take the derivative of that in order to figure out our changes in slope, that kind of complicates things. Yeah, the section after, it's the second logistic regression, it kind of shows gradient descent with logistic regression. Yep. So this plot kind of shows where the logistic regression found to draw the boundary between the two. So this kind of graph you can only make with two features. If we were to add a third feature, the boundary between all the features would actually be a plane. So it increases in dimension each time. So just something kind of cool that you can visualize it. So now we're going to talk about comparing logistic models and also adding more than two features. So this is going to make, I think, 4 features. Yep, so x1 through 4. And now we're going to bring in the train test split because we're going to try to find a model that best fits our data. So we want something that we're not trained on in order to basically validate it at the end. So we'll just do a train test split here. Now we're going to build our base model. This is what you almost always do to start. You need something to compare to. So you want to build a model that doesn't have any changes. It's just the information you were given. So we can see on this, we can use accuracy score. So this is a difference for classification versus regression. We don't really want to do R squared because we're only predicting one of two values, so it wouldn't really make sense. We're instead more concerned if we accurately predict the class of each of our targets. So we can use accuracy score for that. You can see that we got a 70% on train, 68 on test. So like usual, we're probably a little bit overfitted. We didn't do as well on the test set as we did on the train. So now we're going to use recursive feature selection to kind of figure out the best number of features to include. So we only have 4 possible. So it's not very many to compare, but we can still kind of see how the train and the test accuracy changes. So here you can see it seems like with one feature, or actually this should be +1 so that we get 4 there. Okay, so it looks like with one feature, we get the highest test accuracy, but with 2 to 4 features, we get the highest train accuracy. So can someone tell me how many features you think we should select for this? Yep, that would probably be the way to go. So we can go ahead and select 1 then. Let me go back here. Do I have something after this? Hold on. Oh yeah, here. All right, and I think this is just, these are just the accuracies. So yeah, so for one feature would be our best bet because we get slightly higher test accuracy. All right, so now if we want to build a model that has just one feature and compare it to our base model, we could just use, train and test accuracy, or we can use other metrics since we're doing classification. So a big one is confusion matrices. This is a topic you're going to really want to know and understand because you're going to see and use it a lot. So basically, since we have 2 classes, 1 and 0, we can output a chart at the end that tells us how well we did. So across, let's see. So across here, this is going to be what was true. So these are the true values. So true 1 and true 0. And then across here is going to be predicted. So true and predicted. So to fill out, for example, this square here, we would find all the ones that we predicted true that were actual, or that we predicted 1 that were actually 1, and we would write that number here. Then for this one down here, it's all the ones that we said were 0 but were actually true, so false negatives, and then so on and so forth. So you have true negatives, false positives. So it kind of gives you an idea of where your model succeeds. So sometimes a model will be really good at getting all true positives, but won't do well finding all the true negatives. And there's a lot of trade-offs there, which I think we'll discuss here in a second. So first, we're just going to look at some confusion matrices for 3 of our models. So with 1, 2, and 3 features. All right, so hopefully you can see this. But so if we look at the square here, can someone tell me what that represents? Remember, the bottom here is true, and this is what we predicted. So true and predicted. Yep, true positive. And then can someone tell me what this would be here? Yep. And then, you mean with the previous screen? I think they put it on different axes, maybe. It might have been flipped in that graphic. Oh yeah, so down here, yeah, you can see how it's labeled. It's kind of tiny. So true positive, true negative, and then what would this one be here? Mm-hmm. And lastly, this one here. All right, good job. So now if we look at all three of these, what do we notice? So these two are the same. So what's the difference between one feature to two or three features? Mm-hmm. But what else? Mm-hmm. So we have less true negatives. So can anyone think of a situation where it's more important to minimize false positives as opposed to false negatives? For example, maybe something medically related. Yeah. Mm-hmm. So in that case, if you're predicting if someone has a disease, what's most important to minimize, or what's the worst thing to get in that? A false positive or a false negative? Why is that? Right. Yep. So that's probably like the logical conclusion there. There are also like negatives for false positives. I mean, if you tell someone they have the disease, they go through treatment anyways. But yeah, in general, like a false negative would be the worst case scenario. So you can see how, depending on the situation and what you're trying to predict, you might want to minimize or maximize different parts of this confusion matrix. So that brings us to fitting our model then with one feature. And a neat thing about this RFE is that you can call support after it, and it tells you which of the features it included. So this would be X1, X2, X3, X4. So it chose to just use X2 in making its predictions. So that can be helpful for understanding, which features were important and which ones were selected. All right, so that brings us to the topics of sensitivity and specificity. These are really important to know. They're also really easy to flip-flop and mess up, so you have to kind of be careful. But basically, sensitivity is the number of true positives that you predicted correctly divided by the total number of positives. So in other words, it's your true positives divided by what? What would give you the total number of positives? Definitely true positives, but isn't a false positive actually a negative? Yep. I think you're breaking up, Anubhav. It's like a little delayed. But okay, so then similarly, specificity, or I guess oppositely, is true negatives over total negatives. So true negatives, and then what would I divide this by? Yep. All right, so you'll see these a lot. It's basically just another way to measure and compare different models. And it also kind of summarizes the information in a confusion matrix just in 2 numbers. All right, so typically they're inversely proportional to each other. When we raise one, we decrease the other. So there's this kind of trade-off on whether we want to be better at recognizing the positives or the negatives. And so, like I said, what's more important to minimize, false positives or false negatives? It's kind of a question you always have to ask, given the context. For some things, it's really obvious, like medical situations. For others, for example, in like banking, if you're trying to decide whether or not to give someone a loan, there might be arguments on either side for which one you'd want to minimize. But yeah, something to keep in mind. Let's see. Can you guys see? Let me see here. Oh, I need to run this. There we go. All right, so then can someone tell me how to calculate sensitivity given this confusion matrix? Divided by 73 plus 64. So that would be the true that would be true negatives. Yep. So plus 36. All right, so there's our sensitivity. And then what's our specificity? Yep. All right, so we see we got a little bit higher specificity there with 70%. So you kind of just have to know from what it outputs. I think it says it in the documentation when you get confusion matrix from sklearn. But basically the bottom here is, let me open this up. So I think actually, now I think I'm confused because of that other graphic, but I think the bottom is what we predicted, and then on the side is what's true. So this would be, we predicted 1 and it was 1. This would be, we predicted 1 and it was 0. So pred and true. Is that what it says, Beth? Pred on the bottom? Yep, so 0, 0, then this is true negatives. Yep. So then 1 and 0. Yep. So you'll want to just kind of remember that, but you can always reference the documentation if you forget. All right, so now another feature of logistic regression is instead of just getting the predicted class, we can actually get the actual probability that it predicted for both classes. So what you see here are each of our x values, and then in the first column is the probability that it was a 0, and in the right column, the probability that it's a 1. So it basically uses this, whichever one's higher, to ultimately decide which class it's going to predict. So we're just going to focus on positive probability. So the probability is that it's 1. So we're grabbing that second column only. And so these are all the probabilities that it's a 1. So basically at the base level, if it's above a 0.5, then it predicts a 1. If it's below 0.5, it predicts a 0. But what if we wanted to change that threshold? So right now it's at 50. So if we set our threshold to 50, and for each of our positive probabilities, we check if it's greater than that threshold. If it is, we predict a 1. If it's not, we predict a 0. So if we print this out, we'll get all of our decisions that our model would have made naturally. But we can raise this threshold to say 0.75. Now it makes it a little bit harder to score a 1, so we end up with more zeros. We could also make it lower, make it like 0.45. You'll see why we want to do that in a second here. So here we're going to pick a few different thresholds around 50, so 18, 25, 50, 75, and 85. Then we're going to print out all of our decisions for each of those thresholds, make a confusion matrix, and then we're going to calculate the sensitivity and specificity for each of those. So here you can see how the two change. So in the middle at 0.5, we have the results we already saw. It's basically the point where both are maximized. But if we wanted to raise it to, say, 0.75, the threshold, then we would get a much higher specificity, but we would lose out on sensitivity. So depending on what our outcome is and what's important to us, we can modify this threshold predictions to kind of shift it in our favor and to increase either our sensitivity or our specificity. And so what this plays into then is what's known as AUC, or area under the curve, and the ROC plots. So ROC curves show this trade-off between specificity and sensitivity, because usually when you raise one, you lower the other. But on this graph, you have specificity on the y-axis and 1 minus sensitivity on the x-axis. And then the AUC is just the area under that curve. So if a model is basically perfect at predicting everything, it will have an area under the curve of 1, and you'll see why in a second. Whereas a model that's just guessing randomly between 1 or 2 options, it will have an AUC of 0.5, or 50% basically. So this function here will take in a set of x values, y values, and a model, and it will generate the ROC curve for that. So we'll go ahead and store that because we'll use it here. And we'll go ahead and plot that with our test data. So you can see we got an AUC of 0.72, which isn't terrible. It's basically in between 0.5 and 1. 1 would be perfect. So now what you can see here is if we wanted to have a true positive rate of 80, we would find 80 on the left here and go over. And wherever that meets the red line, we would then come down. And so if we were able to get an 80% true positive rate, we would end up with about a 42% false positive rate. If we wanted to go even higher to, say, 95%, and we bring that over and then down, we would see that we would have basically an 87% false positive rate. So the higher we want our true positive rate to be, the higher our false positive rate will be as well. So it's kind of about picking the right point that maximizes this and minimizes the false positive rate. And so if we had perfect predictions, our ROC curve would actually be this kind of upside down L shape. So it would go straight up. So we basically always predict, we always get true positives 100%, and we get no false positives. And then this dotted line is basically just a random guessing. So if it just picked randomly each time, it would have that curve. So if you end up with an ROC curve close to that, that tells you that your model is not much better than just randomly guessing, which would be bad. All right, so one more thing to talk about is class imbalance. So in our example, here's the counts of our target variables, so the zeros and the ones. We can see they were approximately equal. But what happens if one of our targets is very rare. So what if R1 is an event that's super rare? You know, it's some disease that only occurs in 1 out of every like million people or something. So we're going to make a data set to reflect that. So here you can see our ones are 977, and we only have 23 zeros. So now we'll see how a logistic regression model kind of handles that imbalance. So we'll do a train test split, fit a logistic regression model, and print out the test accuracy. So it's 0.985, which sounds pretty good. But then we'll plot out a confusion matrix. Now, does anybody see the problem with this and why a 98% accuracy doesn't really mean anything? So in terms of negatives, we were only 50% at predicting them. So basically just like random guess. So the 98% was inflated because we got nearly all of our ones right. But maybe that's just because our model saw so many ones that it's predicting one for basically everything. So this is a problem that can occur in classification when you have an imbalance in your number of classes. So we can kind of print out the base sensitivity and specificity here. So since sensitivity is to deal with our one value, our one values, it's going to be very high, but our specificity is only 0.5 because it's basically random guess. So we'll store that so that we can kind of compare it here after we fix this problem of imbalance. So a good library for this is called Spout. What it does is it basically resamples your data to increase the number of your minority class instances. So you basically create a SMOT object here. You fit it to your sample. One important thing is you only want to do this set. You don't want to do it. Your test should be like what you're predicting like in the real world, and you don't want to resample and make a bunch of fake points for that. So we fit and create new X-train and Y-train data sets that have been resampled, and then we're going to build a model fitting those to it. We'll give it a You guys, you might have to install it. I think it's pip install imb learn. And then you'll have to re-import everything again in your notebook to get it to work probably. And depending on your computer, it can take a little bit of time. It's usually not too long though. Okay, we're done here. So we'll go on. There we go. Okay, so now we're going to compare our sensitivity and specificity before and after the resampling. So here, actually, I didn't show the one part that kind of confirms what the resampling even does. Let's see. Okay, so this was our value counts before the resampling, and then after, you can see it made it equal. You can change some parameters so that it doesn't always make it exactly equal. It can just kind of increase it a little bit and shorten that distance, but in this case, it just recreated a bunch of 0 instances to kind of match how many we had for the ones. So now we can compare. You can see that after the resampling, we were able to increase our specificity. Not by a ton, probably because we only had a couple instances of 0 anyways in our data, but we were able to, so that can be a really important tool to have if you ever have imbalanced classes. Does anyone have any questions on this before we go on? Mm-hmm. So the AUC is just under the curve. So if we had a perfect scenario, where we had perfectly accurate model, the area under the curve would be 1, because you can see it goes from 0 to 1. So basically, it tells you how close you are to that perfect model. So like this would be an AUC of like, I don't know, 0.8 or something. And then our red line is 0.7. And then the dotted line is 0.5. So it kind of gives you a measure of how close your model is to being a perfect model and being able to reduce your false positive rate while still having a true positive rate. Mm-hmm. So typically the threshold of 0.5 is going to leave you with a point like somewhere here, the point like furthest this direction. But then depending on your situation, if you care more about false positives or false negatives, you can move in either direction, sacrificing something but gaining something else. It's always going to give you the point that's the best for maximizing both equally. Yeah, no, it always seeks to find that middle point where it'll maximize both, and then you can move it to either side if you need to. Yep. Anyone else have any questions before we go into the activity here? All right, so here's the activity. You're going to do basically what we just did, only using some loan data. So this data set basically has information about customers who've taken out a loan before. It gives you, their income, things like that, if they have debt. And then also your target is whether or not they defaulted on a loan that was given to them. So you're trying to build a model to learn this so that when you get new customers, you can predict the chance of them defaulting on a loan. So definitely thinking about the trade-off between sensitivity and specificity is going to be important here. And then just a couple reminders, there's some categorical data in here. I think like one of them is whether or not they've taken out a loan before. You can basically include that in logistic regression just like normal. You just have to make it a dummy variable. And then also, if you have your features in different scales, you always want to scale them. You can just use like standard scalar from sklearn. And yeah, that should be all you need to know. Do you guys have any questions on this before you get started? All right.